Thank you all for attending and for having an interest in planetary protection. So I'm honored to be here today to talk everything planetary protection with you all, and to kind of give you an overview of how we updated our policies at NASA in planetary protection. Since we have a lot of policy students here, I'd like to give you a little bit of a behind the scenes as well of what goes into that process of crafting new policy and getting it released through a federal agency and getting it out there in the world. But first, none of this happens alone. We have a team of folks that have been working for several years in Office of Planetary Protection to help us move this forward and help to update our policies. So see them all listed here. Often these are folks that are behind the scenes, and I'd like to just make sure that they get the credit that is due for helping us throughout several years of updating the policies that you're going to be seeing here today. So let's start off with, what is planetary protection? So planetary protection is the practice of protecting the solar system bodies when we go exploring into the solar system with spacecraft. And that's called forward planetary protection. So you leave Earth, going out into the solar system to explore. We want to be good, responsible stewards of that exploration. Make sure that we're not contaminating those solar system bodies with the materials that we bring on board our spacecraft. So that's forward planetary protection. Second part is backward planetary protection. This is when we're bringing samples back from our exploration. So I think you had a seminar about OSIRIS-REx, bringing back samples from the asteroid Bennu. That is a mission that has, backward planetary protection. Luckily, thankfully, very few organisms just, reporting unrestricted there. But we're also planning for a Mars sample return, which is going to have very, very detailed backward planetary protection. Make sure we don't pose a risk to Earth, life on Earth, humans on Earth. So that's the backward planetary protection portion of it. So it's all about that sustainable, safe exploration of the solar system as we try to find out more about, are we alone in the universe? How did the universe form? Origins of life and potential life in the solar system. So planetary protection is focused on that science that's currently being done, but also enabling future science. So making sure we don't irreparably damage the places that we're visiting for future generations to be able to explore. This is an international process. This is not something new, not something specifically invented by NASA. This has been going on for quite some time. So it's grounded and rooted in the Outer Space Treaty of 1967. There are several articles within the Outer Space Treaty, as I'm sure many of our policy folks in here have seen. And there's two key policies that relate to planetary protection. So the first one, Article 6, is about international responsibility. So the state parties that launch spacecraft, they are responsible for that spacecraft. So whether it's a government agency that's launching that spacecraft or non-governmental entity, it is the state party to the treaty that signed the treaty that is responsible for the actions of that entity. Article 9 is where planetary protection really comes in. So this is the article that has grounded to conduct exploration of the solar system to avoid harmful contamination. So these are the key words in the treaty: avoid harmful contamination, and also adverse changes in the environment of the Earth from any extraterrestrial material brought back to Earth. So Article 6, really, really important for planetary protection. As you can see, though, as a treaty, very broad language. Difficult for scientists and engineers to work to, not really much detail there. So we have additional layers down that help support policy. Next layer down is the Committee on Space Research, or COSPAR. They are an international body. They have a panel of planetary protection that is a panel of international scientists that are constantly meeting to review missions into the solar system, the latest scientific discovery information about what's being discovered in the solar system, and help to set international consensus guidelines. So they set guidelines agreed upon at the international community level for how everyone is going to work together in this realm. Now, the entire solar system, very, very large, and it is not, all target bodies do not have the same requirements. So COSPAR came up with a method to categorize, depending on the target solar system body to be visited and studied, what's being done there, And they have categories 1 through 4 for that forward planetary protection and 5 for the backward. And I'll show that in a little bit more detail later. So that's COSPAR as that guideline international level. Also still very, very broad, still, at the guideline level. So next layer down, we get into space agencies like NASA. This is where, we definitely are a participant on COSPAR. We support this whole international consensus process, but we take their guidelines and then we help break it down into further roles, responsibilities, requirements on our side for, okay, here's how we're going to conduct our NASA missions and do it in a way that we are in partnership with the international scientific consensus process. Also, depending on what we learn on our missions, we'll also flow information back up to COSPAR and say, hey, here's some new information that was gained. Here's something for you all to consider further to revise guidelines or to provide additional information to the scientific community. So there's definitely a circular, forward, backward between NASA and COSPAR in our working relationship in working through the changes for planetary protection. So as I said, mission categories, this is how we slice up the solar system and look at it for planetary protection. Not all solar system bodies have the same level of sensitivity. So first we have category 1. This is the lowest level. So this is where these are bodies that don't have a biological contamination concern. And they also are not a body that we're concerned about for understanding origins of life in the solar system. So think Earth, Earth orbit, things like that. Category 2 starts to get a little bit more sensitive. So still not a concern from biological standpoint where our spacecraft could biologically contaminate that body. But there is interest from a chemistry standpoint of understanding life in the universe or understanding, areas of scientific interest of how the universe formed. Earth's moon is part of this, and Earth's moon actually has 2 additional subcategories that COSPAR helped to create depending on the permanently shadowed regions. You got those icy regions on the moon, and those are a concern from an organic contamination standpoint because in those cold regions, the spacecraft lands, releases molecular contamination, those contaminants could then deposit cryogenically, in those areas, settle in those cryogenic sensitive areas. And so scientists probably want to know that when they go to those areas to do ice core sampling to understand more about the studies, are any organics that they see there due to spacecraft or due to chemical processes happening within the solar system. So that's category 2. Category 3. Now getting in more sensitive. So these are for target bodies that do have a serious risk of contamination from a biological standpoint, and they're also significant for understanding origins of life in the universe. There are 3 sensitive solar system bodies right now. Others could be, determined by COSPAR later, but currently there are 3: Mars, Europa, and Enceladus. Category 3 is for anything that's doing a flyby or an orbit of these type of bodies. So the concern here really is crashing into these systems and depositing like a dirty spacecraft onto the surface. So that's category 3. Category 4, same thing, same target bodies, same sensitivity, except for now the spacecraft is landing, probing, roving, and even flying helicopters on the surface. So again, this is Mars, Europa, and Enceladus, but now you have a much more high interaction with the surface. So higher and higher potential for contamination. So this is all the categories for forward contamination, meaning anything contaminant-wise we deposited on the spacecraft here on Earth, transferred to the target body for planetary protection needs to take care of. Back planetary protection is where category 5 comes in, anytime we're bringing samples back. And there are 2 categories here. There's unrestricted, just like OSIRIS-REx, where samples are coming back. There's no risk to Earth life from these samples coming back. Samples can come back. Scientists can do science on them. All good from a biological safety standpoint. Restricted is where there could be a biological concern. So this is where Mars sample return falls in. Apollo originally had a restricted category 5 Earth return until later it was determined lunar samples aren't an issue. So that later switched over to an unrestricted. But restricted is where you have to worry about the safety of Earth, Earth life, Earth's biosphere. So having specific safety protocols in place when those samples come back until all the assessment is done to say, okay, it is now safe. We can do, additional science in a different environment with these. And I'll show a little bit more detail of what that looks like. But those are the 5 categories for planetary protection. So how do you do this categorization? Well, it's not only a matter of looking at the target body. Target body is definitely a concern here. But it's where is the mission going for that target body? How's it going to get there? What trajectory is it going to take? And then what's it going to do once it gets there? The mission operations. Any one of those 3 could drive to a more sensitive category. So you may have a target body that you're going to, such as an asteroid far out in the solar system, but you're going to do a Mars flyby. You may have to go to category 3 for Mars because you're going to get very, very close to Mars during that flyby for that asteroid, which might be a category 2 or category 1. So these 3 things have to be considered when we're categorizing our missions. So right now, Office of Planetary Protection is keeping an eye on everything going on in our solar system for NASA. These are the current mission categories for everything that we are tracking. The ones in purple are missions that have not yet launched. And I've highlighted a couple of situations where the categorization might be a little bit different. So for example, Parker Solar Probe is, anything going to the sun, category 1. However, they did a Venus flyby. Venus is category 2, so that drove them to a category 2. Mars 2020, definitely a big one there. That one has our rover, the Perseverance rover on the surface of Mars right now. So that has a sensitive category 4, and there's subcategories for Mars, 4B. And it's going to have the restricted category 5 Mars sample return. OSIRIS-REx is category 2 with that category 5 unrestricted Earth return. Psyche is going out, mission to an asteroid. Again, lower categorization there, but they did that Mars flyby. So that forced them into the category 3 section there. New Horizons, same thing. Going out to the Pluto system, so they ended up category 2. So Office of Planetary Protection has a lot going on. Even though our Mars missions very, very near and dear to our heart, we do have to worry about the entire solar system. So this is keeping us quite busy right now. Okay, so jumping into the policy side of the house. This is the trail map, as we call it, of all of our planetary protection policies for NASA. And so I'll step through each one and kind of give you a really quick overview. It can be difficult, I know, online in a federal system to find where documents are. So we developed a nice, easy QR code that takes you to our website to pull up these documents, which you can read if needed. So at the very, very top, we have what are called NASA policy directives. This is the very broadest level of policy. And for us, we are in the Office of Safety and Mission Assurance. And this policy document under Office of Safety and Mission Assurance says we will be doing planetary protection, as part of our policy. So it's very broad. It's a one-liner in there mixed in, but we are included at the very, very top level. Next, we have what's called a NASA Interim Directive, or a NID. This is a temporary document. This is for when you need to put policy out there in a short term, in a short amount of time. It's very short, quick turn, gets a policy or requirements out there, but it's meant to be temporary. So for us, we have this for our crewed plans for planetary protection for human missions to Mars. So you look at this document, it's very, very broad. It says, yes, we're going to be considering these things for planetary protection for future human missions to Mars, but we still have some work to do. And so this one, you can almost kind of think of this is the placeholder document temporarily in place. It says, yes, we are working on it, but we still have some work to do before we can make this a permanent policy. So it's green on this slide here because it's currently being updated. it will actually eventually roll into the next higher level here. So next we have our procedural requirements. These are our roles and responsibilities. That's the easiest way I can describe this. This says, who's responsible and what are they responsible for planetary protection. So it's a high level, policy, but it says, here are the folks that are responsible for specific roles in helping us to implement planetary protection at NASA. And I'll show this in a little bit more detail later. The NASA standard, that's where all the scientists and engineers go. That's where the technical requirements are. So all of the shall statements in policy world, right, of you shall do this, that's where all those requirements lie. You'll notice that the NPD, NPR, and standard all have very, very recent dates on them, 2021, 2022. That's how recent we've been going through this process of updating and overhauling these. So these are still very, very new out there in the world. And we got to the point where we said, you know what, we need to get these new policies out here, get the community using them, and then we can take their feedback and update them in the next round. So that's currently what's happening with those. Last one we have is a NASA handbook. You'll notice the date, 2010, very, very old. A handbook is really just guidance. It's the how-tos. You might want to consider these things for your missions. This was for us more important to get our main policy documents updated. We're now directing our attention to updating this handbook, getting it out there, getting it published to help the scientific and engineering community work to good engineering and science practice for planetary protection. So that's the plan for the handbook. So that's a little bit of the trail map here. And today I'm going to be focusing on the roles and responsibilities and then the technical requirements. So the NPR and the NASA standard. Okay, so when these things are applied to missions, this is what it looks like for forward planetary protection and controlling contamination of solar system bodies. Very much follows the NASA systems engineering and project management process. This was by design. This was one of the major updates that we had to make to our policies, was to align planetary protection to the existing NASA infrastructure. Previously, it was outside of that structure, makes it difficult for projects and engineering to work with that discipline. And so that was a major overhaul of the policy, was to bring it into the normal fold and bring it into the rules and responsibilities. So you'll notice forward contamination control follows the normal mission life cycle. So you begin with that categorization process and designing the mission, designing the spacecraft. Then you get into actually building the hardware. That's the assembly, test, how it's going to be transported, how it's going to be launched. This is where the rubber hits the road. This is where contamination on Earth is going to happen. It's going to happen in all of the labs, in all of the environments where this assembly and integration and test is happening. This is where you also introduce all your mitigation activities. So clean rooms, cleaning of surfaces, baking out of components, all of these mitigation techniques to help control contamination to acceptable levels. Once the spacecraft launches, now we're into, please don't hit anything that we really care about out there in the solar system. So avoiding that inadvertent impact when launching. This not only goes for the spacecraft, this goes for any secondary payloads that are riding along with. We're seeing a lot more of ride shares happening where a main spacecraft is going, dropping along folks along the way, kind of taxi ride way of going. So all of them also have to worry about, cleanliness and contamination. Then also the rocket that's used to launch these spacecraft. Once it's spent, making sure that spent rocket does not hit somewhere like Mars, Europa, Enceladus, etc. All of those are calculations that have to be considered. Once the system has landed for those landed missions, avoiding contamination of the surface it's interfacing with. So avoiding contamination when digging into surfaces like the Mars InSight mission, or for like Curiosity and Perseverance, the rovers that are up there right now, avoiding contamination as they rove along the surfaces. And then finally, end of mission disposition. So this is when everything is done, everything is over with. What happens to that spacecraft when it gets to the end of life? Rovers on the surface of Mars usually stop where they are. They have that slow, quiet, just like we saw with Opportunity, turning off of all the batteries and everything. InSight, a lander, so we know where it is, but knowing where spacecraft end up at the end of the mission. If it's an orbiter, knowing where it might deorbit and what it could possibly crash into. There's an analysis that's done that's called a burn up and breakup analysis for things like, orbiters at Mars. Are they going to break up sufficiently as they deorbit? Also of note, the Cassini mission had to do an end of mission disposition. So Cassini witnessed the plumes of Enceladus, and scientists said, wow, those plumes are really interesting. We don't want to contaminate Enceladus. So we're going to use what propellant is left. And Cassini had its end of mission into Saturn to make sure that it wasn't going to drift and end up accidentally crashing into Enceladus. That's the forward side. The backward side, we start again with the mission categorization. This is very easy for the unrestricted missions. They just get categorized as unrestricted and they're done. No more requirements for them. Bring your samples back, have fun in the lab, go and find out really fun, interesting new things in that science. The restricted Earth return missions, though, have to follow this process. So they get categorized as a restricted Earth return. There is a contamination avoidance prior to Earth entry. So avoiding, unsterilized Mars particles from ending up, in orbit, as it were. Also avoiding contamination during Earth containment. So for Mars sample return, we're going to have a ballistic re-entry of the Earth entry system landing on Earth. And so making sure that whole spacecraft, that Earth return system, is going to remain intact during that whole return to Earth. And then once the samples do get returned to Earth, pick them up, bring them into biologically safe laboratory, and then doing a sample safety assessment. So safety assessment happens first. Make sure, out of abundance of caution, everything looks good. We don't think we're going to see anything, as far as Mars biology goes, but out of, just being safe, we're going to do our safety assessment, make sure, and then once that's good to go, then, science will be going through, their scientific study process. So that's backward contamination. These are the table of contents for the NPR and the standard, just to show the different focus for each. So like I said, the policy, the NPR, this is the roles and responsibilities. You'll notice that there are 5 people listed there, much more than 1. You might think, oh, it's planetary protection. Only the planetary protection officer would have a role. That's how it used to be in our policy. And in this whole restructuring process to bring planetary protection into the normal NASA infrastructure of systems engineering, project management, there are now others that are involved and have a role. So the mission directorate associate administrator, the NASA project manager, our planetary protection officer still, which is under the chief of safety and mission assurance. And then finally, that technical authority person on the project for safety and mission assurance also has a role. So much more expanded, many more people now have a role in planetary protection at NASA. And then also the procedural requirements I talked about earlier are given there. The standard, which is much more lengthy document because now we get into the technical requirements, follow that flow of controlling forward contamination and then prevention of backward contamination for those Earth return missions. You'll notice that there is this really odd chapter 6 sticking out here, the NASA spore assay as a chapter. So the NASA spore assay has been around for a very, very long time, decades, 1960s-ish. And this is a way to quantify biological contamination in terms of bioburden on a spacecraft. And this is worrying about what is the hardiest thing we think we can send into space that's going to survive the entire time, and that's spores. So the spore assay is a way to quantify the amount of biological contamination on the spacecraft that might survive that entire trip. Previously, that process was contained in the handbook. And I always tell people the handbook is something that it's just, good practice. You can actually toss the handbook away and not even read it. Totally fine. The things you do have to read are the policy and the technical standard. You can't throw these 2 documents away. So because of that, because the NASA standard spore assay is so key to quantifying biological contamination for spacecraft, we had to codify it and pull it into the technical standard, which is where it exists today for now, until an industrial standard comes along and we can remove it from this document. So why the heck are all of these policies and documents needed? Well, remember that the purpose of policy and the reason that we have policy is that it helps to convey the intent of leadership and sets the direction for the organization. So for planetary protection, all of our policies say this is how we're going to conduct planetary protection at NASA. And it's really based on risk. How much risk can be tolerated for the mission? That's very, very different depending on the mission, depending on the time. What we did for Viking is very, very different than what we do today with the Mars Perseverance rover, for example. And that's going to be very, very different from what we do in the future when we bring humans to Mars. So it all depends on that mission and the current scientific knowledge, which, as we know, is always changing over time. The procedural requirement, that roles and responsibilities, that's all about someone making a decision about something. So who are the players? And that's why all of these different roles are defined. And what information do they need to make a decision? That's really what this policy document is going all, is providing to the community. So for those that aren't as familiar with NASA structure, we have the programmatic side, which is like what we have listed here, our mission director, associate administrator, and our project manager. They're the ones that are really running that whole mission, making sure that it's going to, get assembled in time, get tested in time, launched in time. And then on the other side, we have the technical authority. So independent technical authority, we're the ones overseeing the whole process. We're not there in the day-to-day because we can't be. We can't be down at that detail level. We got to keep the broad view in mind for the agency. And so that's why it's important to have these two roles as part of NASA's planetary protection policy. And then finally, the technical standard, that's the source of the requirements, the technical requirements for the science and engineering community. It is not one size fits all. We have started to shift the culture from what are called prescriptive requirements, which is you shall do this in this manner and this manner only, very, very prescriptive, versus performance-based, which is here's the end goal. You can get there in any way that you wish, but you still have to reach the goal. Very, very big shift. And our culture is still changing at NASA, trying to wrap our head around it. And that's very much currently our role in the Office of Planetary Protection is to help this. The missions are responsible for identifying the relevant planetary protection requirements for their missions. They know their missions best. They know the science they want to do. So it's all on them to help determine, what are the relevant requirements for planetary protection that are going to enable their mission. Again, planetary protection is all about enabling the science. And then Office of Planetary Protection, our role is to provide guidance of the overall process, and we're the systems of checks and balances, just to make sure that what they're doing is appropriate. So they can come up with a wild new way of doing something. That is great. We're going to ask for the evidence for them, provide the evidence that shows this great new thing you want to do is going to be appropriate and accurate and verified. And it's in line with current scientific thinking. So oftentimes we bring in the scientific community and say, hey, here's this new approach. What do you think about it? Please give us your independent view of this, because Office of Planetary Protection, we're not the scientists day to day working these missions. We need to pull those folks in, get that perspective as we're running our checks and balances to make sure what's happening is appropriate. So the motivation to change, like I said, we overhauled a lot of our planetary protection policies. Why would we go through this process? Why wouldn't we just leave it the way it was for so many years? And the reason is we have new folks entering the whole realm of providing space exploration and instruments and vehicles for exploring in space. So you have a lot more participation in the commercial and private space industry. So we needed to update to reflect that. We have a lot more missions utilizing small sats, CubeSats, helicopters on Mars. That was new. So things like that, innovative things like that are going to keep coming up. So we need to have a flexible policy that allows for that. And then finally, we're having humans go to the moon again. Humans are going to be going to Mars in the future. So because of that, we need to start planning now for these crewed missions. Planetary protection does not say humans cannot go to these, humans cannot go to Mars. No, that's not what we're saying. We're saying, yes, humans can go if we can monitor and manage contamination correctly. So we're shifting now from what we did with robotic of controlling contamination to managing and monitoring for those crewed missions. And our policies needed to change for that. Also had to streamline what was required as far as deliverables and when. So making sure it's clear to the mission providers. Here's the documentation needed for planetary protection at those systems engineering gate reviews. Here's the deliverables required. As I mentioned, this is a huge culture shift, culture change that is still happening. It takes several years to change a culture. So we're still letting people know that our new policies are out there, and we've completely changed the way of doing business in planetary protection at NASA. And this allows for brand new approaches, like I said. So moving on eventually from that NASA standard spore assay to techniques like metagenomics that's where we want to go. We want to enable technologies like this for planetary protection. And so changing our policies to allow this, so we're not a roadblock to this new innovative way of doing things. Okay, so that's kind of the whole backstory of our policies, the issues, why we had to change. So now I'm going to give you the backstory and behind the scenes of how all of this change actually occurs. So first, it begins with a vision. It doesn't begin with writing. Writing happens later. You have to start with a vision for the organization. So for us, we had to sit down, really think about what is our philosophy for planetary protection at NASA. What do we want our future state to look like? We know what our current state is, but now we want to change our policy to enable a future state. What does that new future state look like? How do we get there? That's the purpose of having a vision. Next, coming up with objectives. This is also really important before even starting any of the writing process. So breaking things down from that vision level to the next layer down of thinking about, okay, what are my objectives to get there? What are my individual steps that I need to do to get to a final policy? Also, this is where we did a lot of logic diagrams and flow charts, just talking about major things in our policy before we put pen to paper. If you start writing too quickly without sketching things out in a logic flow diagram, you end up having to delete all that wording anyway. So we found logic flow diagrams and flow charts to sketch these things out. Mind maps, great way to do things before starting the writing process. And then writing. This is where we had a small team, 5 to 6 people on average, in a meeting, group writing. I know that like makes people think, oh my gosh, that's like nails on the chalkboard here, right? Like group writing. But this is how we did it. We actually had that multidisciplinary group of people together in the room, working together to write down. And sometimes it was like, you got one sentence that day. Sometimes you got entire paragraphs down. Sometimes you were tripping up over one word, scrutinizing a single word and having to think, wait, is that the word we want? Or do we want a different word? We may have to go ask a different community, like science community, is this a word we want to use? So it's a lot going into that whole group writing process. And then editing usually is happening naturally as part of that writing process. So we were often editing in real time as we were writing new policies. Then there's an internal review that happens. So when you get your documents to a point where you can see the entire document, see how it flows together, as the writing team, you are now too close to it. You cannot see spelling mistakes. You cannot see logic mistakes. You have to do the review together, but then you have to get it out there, get it out to different people that haven't been staring at that document to find where does it make sense, where does it not make sense, where does it need to change. Then you go to the agency review. So now this is where our policies go out to all NASA centers, and they have a couple weeks to take the document, review it, provide feedback. So this can be folks, at any NASA center that are looking at this document, fresh eyes, new look at it, and they're going to give back a ton of comments. So for the policy document, we had about 200 comments come in. For the technical standard, once the engineers and scientists got a hold of it, we had 900 comments come in. 900 comments for a team of 6 people is a lot to deal with. So, and you have to go through every comment. You have to dispose of every single comment that was received on that document. So what we did is we found there was a lot of overlap. So we did a process of bucketing, grouping comments, like comments together into buckets. And then we even did a subdivision from that of pails. That's what we call it. So we had buckets and pails to break these comments down. That was the only way a small team of people could get through that many comments. And a lot of times, I mean, there was a lot of folks that, had just seen these documents for the first time and weren't aware of all the changes and weren't aware of all the past history. They were just seeing the document for the first time, providing their comments. So that led to communication. We held a lot of communication events. We talked to groups of people, subgroups of people. We held town halls with focused, folks at the different NASA centers to explain, okay, we've received your comments. Here's how we addressed your comments. And here's what we meant by, the resolution of your comments. So some folks, it's like, we're gonna have to break your heart a little bit. We're gonna have to say, no, we're not gonna accept your comment, but here's why. And when you explain the why to people, then they're like, oh, okay, I understand now. I'm on board with you. This part is a lot of work. This is where you get out of the technical realm and you get into the, working with people, developing relationships, communicating effectively. You have to win people over in this process, because you can have one group that still says, nope, I don't agree, and I'm not going to concur on your document. You have to get there. So this is a huge lift required of talking to people. And sometimes, again, it came down to a single word in a paragraph that was holding up the entire process. But you had to get to that eventual understanding with everyone. And then finally, you reach the final step, which is agency concurrence. That's where all groups that are in part of the review process have that review authority sign off, and it goes to the administrator for sign off as well. And then that's when the document gets released and published in the NASA system, where everybody in the public can now access it. Lots of steps. So this is what's happening. This process takes years. Takes years to write the documents. Took about a year for each to go through the review process. Takes a couple months just to go through the communication process and the final concurrence process at the agency. So folks will say, NASA, you're so big, you move so slow. Why does it take you so long to do these things? This is why, because we're involving so much of the community in the process. All of these perspectives, all of these thoughts that went into the comments, very, very valid. And we wanted to consider everything. But at the end of the day, you do have to make a judgment call and move forward with the document. So we know it's not 100% perfect. Yes, I'm going to admit, we put policy documents out there that are not at 100%. We had to get to where we felt we were at about the 80% level with our documents, because you can never achieve perfection. And there was so much that we needed to have changed for so many key missions. We just said, it had to make that call and say, for right now, where we are, it's good enough. We need to put it out there. We need people to start using these documents. We need to get additional feedback from these new policies being used. Requirements, they need to be put to use in order for people to identify this works, this doesn't work, this is what needs to change. And that's where we currently are in that process. Areas where we know we need to work more, that backward planetary protection, documentation for Mars sample return. So Mars sample return, very much still concept, design phase. There's going to be a lot of paperwork that comes with this whole process. And it's not going to be just NASA involved in that process. It's going to be an international process. So what does that paper trail look like to show the samples that we're bringing back are safe and the international community is on board? As I said, planetary protection for crewed missions, we have that temporary document in place right now, kind of some top level goals and objectives, but we want to start getting to those nitty gritty, more detailed requirements for our crewed missions. Assurance case is something a little bit new, something new to planetary protection, but has been used in the safety industry for quite some time. We've adopted this for our documentation and our standards. So this is where, if you have a new way of doing things, if you want to show you're meeting a requirement, you can do it through this assurance case method, which provides, here's all the evidence, here's all the test data that I'm showing that I meet the requirement and I meet the overall intent of the system. So working through more detail on that. Period of biological performance. This is again where we're working with the international community of COSPAR for, are we still within the period of biological performance for some of our missions, or do things need to change here? The NASA standard assay, as I mentioned, that one from the 1960s that's still out there and still documented in our standard. The goal is to get that into an industrial standard. So if industry pulls us into their way of doing things, creates an industrial standard, we'll then cancel that chapter out of our technical standard. Very similar to what was done with clean rooms. The government had a federal standard for clean rooms that eventually got turned over to an international ISO standard. And that federal standard was canceled once the international standard went into creation. Mars sample receiving facility, we have some ideas here, still not codified in great detail. So still working this in our technical requirements. And looking at, how we how we do the organic archiving and inventory for missions. So right now we have a requirement for Mars missions, especially for doing an inventory and archive of samples of spacecraft material. How long do we need to keep that? Where do we need to report this information? Who's using this who could use this information for additional analyses to help with requirements? So that's another area we want to look at. Finally, love this. This is our information for our planetary protection website. We've been doing a lot to try and put information out there to the public about planetary protection. The very, very basics even of like, what are spores? What is planetary protection 101? An article I love, what is the difference between planetary protection and planetary defense? You'll notice I didn't talk about asteroids hitting the Earth. That's because that's planetary defense. So we always tell people planetary defense is worried about protecting the Earth from large objects, large solid objects. Planetary protection, we're worried about the small, squishy microbiology type things. And we've also been putting together quite a few educational videos. Again, our information is public, so we can put these videos out there. We can share them with the public. There isn't any, proprietary information that has any issue because we're NASA and we like to share things, with the world. So that's those are all available out there on our NASA website.